we're going to take a journey to the one place in the universe where the rules simply stop working. A place darker than dark. A place where light itself gets swallowed whole and never comes back out. We call it a black hole, but that name barely captures what's actually waiting there. Because falling into one isn't just falling into emptiness, it's falling into something that bends time, stretches matter, and erases the very idea of forever as we understand it. Picture a star millions of times heavier than our sun, collapsing in on itself until it becomes smaller than a single city, smaller than a single street, until all that mass, all that unimaginable weight is crushed into a point so dense that space itself curves around it like water circling a drain, trillions of tons compressed into nothing. And here's the thing most people don't realize. Somewhere out there, right now, something is falling into one of these places. And what happens to it next is far stranger and far more unsettling than anything you've been told. By the end of tonight, you're going to understand exactly why crossing that final boundary might not feel the way you expect, why time itself would seem to slow to a whisper, and why the true horror of a black hole isn't the violence people imagine, but something far quieter, something almost gentle. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Somewhere in the endless dark, gravity is about to teach you what silence really means. Let's start at the boundary itself. Not the star that collapsed, not the moment of creation. The line. Because before we talk about falling, stretching, or disappearing, you need to understand the one feature that makes a black hole different from anything else in the universe. Scientists call it the event horizon. And once you understand what it really is, you'll never think of empty space the same way again. Here's the strange part. The event horizon isn't a wall. It isn't a surface you could touch or a shell you could knock against. There is nothing physically there. No structure, no material boundary of any kind. If you were drifting toward one in a spacecraft, sensors wouldn't detect a barrier. Your instruments wouldn't spike or flicker. And yet, this invisible line is the most absolute boundary that exists anywhere in the cosmos. More absolute than a locked door. More final than the walls of a prison. Because once you cross it, there is no version of physics, no amount of thrust, no engine ever built or imagined that could bring you back. Think about what that actually means for a moment. Everywhere else in the universe, distance is negotiable. You can always, in principle, turn around. Burn enough fuel, wait long enough, travel far enough, and you can return home. But the event horizon breaks that rule completely. Beyond it, every path, every direction, every possible trajectory leads only inward. Forward in space becomes identical to forward in time. You could not turn back any more than you could turn back from next Tuesday. That's not a metaphor, that's the actual physics of the region, beyond the horizon. So what draws this line? Gravity. Extraordinary, almost unthinkable gravity. To escape any gravitational pull, you need a certain speed, what scientists call escape velocity. Leave Earth's surface at 11 kilometers per second, and you're free. Leave the sun's surface, and you'd need over 600 kilometers per second. But at the event horizon of a black hole, the escape velocity equals the speed of light itself, 299,792 kilometers per second. The fastest anything can travel, anywhere, ever. And even that isn't enough. Here's the thing most people don't realize about that number. Light doesn't struggle to escape a black hole. Light doesn't slow down or get pulled back like a ball thrown into the air. Light simply has nowhere to go that isn't inward. Space itself, at the horizon, is bent so completely that all directions curve toward the center. Imagine standing at a place where every single path, including the one behind you, leads to the same destination. That's not a strange coincidence of physics. That is the event horizon. Now picture the scale of what creates this. A black hole born from a dying star might contain the mass of 10 suns, crushed down into a sphere just a few tens of kilometers wide. A city-sized object holding the weight of 10 entire stars. And at the center of most galaxies, including our own, sits something almost incomprehensibly larger. A supermassive black hole, millions or even billions of times heavier than the Sun. Its event horizon alone could stretch wider than our entire solar system, billions of miles across, a boundary so vast it would take light itself hours to cross from one edge to the other. And yet, from a distance, none of this announces itself. That's part of what makes a black hole so unsettling. There's no glow at the boundary, no warning sign, no shimmer marking where safety ends and inevitability begins. Just profound, patient darkness, surrounded by the faint light of matter, still orbiting outside, unaware of how close it is to the edge. Complete silence, no signal, no structure, nothing to indicate that this particular patch of blackness is different from any other, until you're already far too close to matter. This is what makes the event horizon so quietly terrifying. It isn't loud, it isn't violent, not yet, it's simply final. A boundary drawn not by walls or matter, but by the shape of space and time themselves, bent past the point of return. You wouldn't feel a jolt as you crossed it, you wouldn't hear an alarm. In fact, and we'll come back to this, you might not even know the moment it happened. Before we go further, sit with that idea for a moment. Somewhere in the universe, right now, matter is crossing that exact line. Dust, gas, perhaps even the light of a long-dead star, slipping past a boundary with no signpost, no resistance, no second chance. Gone from our observable universe forever, while everything around it continues exactly as before. And that raises the real question we're here to answer tonight. If the boundary itself is silent, invisible, and undetectable, what does it actually feel like to approach one? What happens to matter, to time, to a body in the moments just before that line is crossed? Because the closer you get to a black hole, the stranger the universe begins to behave. Gravity stops acting like the gentle, uniform pull you've felt your entire life. It becomes something else entirely, something that pulls differently on different parts of the very same object. And that difference, subtle at first, is the beginning of everything that follows. For now, simply hold this thought as we drift closer. Somewhere ahead, invisible and waiting, lies a boundary with no return, and we are moving toward it. We are still drifting closer, and something curious begins to happen long before we reach that final boundary. The light around us starts to misbehave. Not disappear, not dim. Misbehave. It bends, it curves. It arrives from directions that shouldn't be possible. And this is where the true strangeness of a black hole begins to reveal itself, well before the point of no return. Just outside the event horizon lies a region scientists call the photon sphere. Here, gravity is strong enough to force light itself into a perfect circular path, orbiting the black hole again and again, like a coin spinning endlessly around the rim of a drain. Think about that for a moment. Light, the fastest thing in existence, trapped in a loop, circling forever, never falling in, never escaping. If you could somehow stand at this exact distance and look sideways, you could, in theory, see the back of your own head, your own light bent all the way around, returning to your eyes. This is not science fiction. This is confirmed physics, and we've actually seen evidence of it. In 2017, astronomers pointed a network of telescopes spanning the entire planet at a supermassive black hole nearly 55 million light-years away, at the center of a galaxy called M87. 2 years later, they released the result. A glowing ring of golden light wrapped around a perfect silent circle of black. That black circle wasn't simply the black hole. It was something scientists call its shadow, a region roughly 2.5 times larger than the event horizon itself, carved out by light, bending so violently that nothing behind it could ever reach our eyes. Here's the thing most people don't realize about that image. The glowing ring wasn't light escaping from inside the black hole. It was light from hot, swirling matter, gas heated to millions of degrees, orbiting just outside the edge, bent and stretched by gravity into that unmistakable halo. Some of what you're seeing in that ring is actually light from behind the black hole, curved so extremely around its mass that it appears to come from beside it, or even from the far side, facing away from us entirely. Space itself acting like a lens, folding light around an object so dense it shouldn't allow any image to form at all. And this bending isn't limited to a thin ring. Picture a flat disk of glowing matter circling a black hole, the kind you've likely seen in illustrations. From a distance, gravity would warp that disk so severely that you would see it not just around the black hole, but seemingly above and below it too, as if the black hole were wearing a halo on every side simultaneously. Light from the far side of the disk gets lifted up and over the black hole's silhouette by the sheer curvature of space. Nothing about this would look natural. Nothing about this would look like anything else in the observable universe. What's genuinely unsettling is what this means for perception itself. Near a black hole, the universe stops behaving in straight lines. Direction becomes unreliable. A single point of light might reach your eyes from multiple bent paths at once, creating duplicate images of the exact same star, stretched into rings or smeared into arcs. Astronomers have a name for this effect when it happens on a smaller scale throughout the universe: gravitational lensing. But near a black hole, that lensing isn't a subtle distortion of some distant galaxy. It becomes the dominant law of sight itself. And yet, despite all this bending, all this trapped and looping light, the very center remains untouched by any of it. Perfectly, uniformly dark. Because no matter how light bends, twists, or loops around the photon sphere, none of it ever comes from within the event horizon itself. That boundary we described earlier doesn't just trap objects. It traps every photon, every particle of light, absolutely. The shadow you see in that famous image isn't an illusion or a limitation of the telescope. It is the literal silhouette of a place where light has permanently stopped existing for the rest of the universe. Think about the strangeness of that. Everywhere else, darkness usually means the absence of a light source. Look into a dark room, and there's simply nothing there emitting photons. But this darkness is different. This is a place where light exists in abundance nearby, swirling, glowing, heated to unimaginable temperatures, and still none of it can illuminate the center. It's not an absence of light. It's a trap so complete that light becomes irrelevant to what lies within. This is also why, despite thousands of black holes suspected throughout our galaxy alone, we've only ever directly imaged 2. Not because they're rare. Estimates suggest our galaxy alone may contain over 100 million black holes drifting silently through the dark. But because most of them show us nothing at all. No glowing ring, no halo of trapped light, just an absence indistinguishable from empty space, unless something happens to be orbiting close enough to betray its presence. And that raises an uncomfortable thought as we continue drifting inward. If light itself struggles this violently just to escape the region outside the horizon, bending, looping, sometimes trapped forever in that photon sphere, what does gravity actually do to something with mass? Something solid, something like you. Because light has no structure to be pulled apart. No front and back, no head and feet, nothing for gravity to grip unevenly. You do. And that difference, the simple fact of having a shape, a length, a body extended through space, is about to matter more than anything else in this story. So let's say you have a body, a shape, a length from head to feet, extended through space. And let's say, for the sake of this journey, that you are now falling. Not jumping, not being launched, simply falling. The way an apple falls from a branch, the way a stone falls from a cliff. And here is the first truly strange thing about that fall. For a while, you wouldn't feel a thing. This idea confuses almost everyone the first time they hear it. So let's slow down. You might imagine that falling towards something as violent and extreme as a black hole would feel like being crushed immediately, like slamming into an invisible wall of force. But that's not how gravity works. Not for you, not for anything in free fall. Gravity isn't a push. It isn't a pressure pressing against your skin. It's closer to something you fall through, weightlessly. The same way astronauts float freely aboard a space station. Not because gravity is absent up there, but because they are falling continuously, endlessly around the Earth. Here's the thing most people don't realize. If you were falling toward a sufficiently large black hole, particularly one of the supermassive giants sitting at the center of galaxies, you might cross the event horizon itself and feel nothing unusual in that exact moment. No jolt, no resistance, no sudden crushing weight announcing that you've just left the observable universe forever. Just silence and the sensation of drifting, the same as falling through empty space anywhere else. This is what physicists mean when they describe general relativity's strangest promise. Locally, in the smallest space around your own body, free fall feels identical to weightlessness, no matter how extreme the gravity generating it. Think about how unsettling that really is, the most irreversible boundary in the universe, and it can be crossed in complete silence, without a single physical sensation marking the moment. You wouldn't hear an alarm, you wouldn't feel a wall, there would be no flash of light, no vibration, no resistance pushing back against you. One instant you're approaching a boundary, the next instant you have passed it, and from the inside, absolutely nothing would feel different in that immediate moment. And yet something profound has already changed, invisibly, permanently. Because the moment you cross that horizon, every direction you could possibly travel, forward, backward, sideways, upward, all of it now leads only toward the center. Not because something is pushing you there, but because space itself, the very fabric you exist within, has been bent so that inward has become the only direction that remains. It's a bit like realizing that every hallway in a building, no matter which door you choose, now leads to the exact same room. You haven't been shoved there. You've simply run out of alternatives. This is part of what makes falling into a black hole so quietly disturbing, rather than dramatically violent, at least at first. There's no dramatic struggle at the threshold, no desperate final battle against the pull. Just the calm, seamless continuation of a fall that began long before, one that simply changes character, invisibly at a boundary with no physical marker at all, complete silence, no signal, no sensation announcing the most significant threshold a person could ever cross. But don't mistake this calm for safety. This is precisely why the event horizon is so treacherous, so quietly merciless. A cliff edge, at least, gives you a visual warning. A crumbling ledge, a drop you can see coming. The event horizon offers none of that. It is invisible by definition, undetectable by any local measurement. A boundary that exists only in the relationship between where you are and whether escape remains mathematically possible. You could be drifting peacefully, watching stars pass by exactly as before, and still have already crossed into a region from which nothing, not light, not matter, not information itself, can ever return. Now here's where it becomes genuinely science, not speculation. Physicists describe this using something called a world line, the path an object traces through both space and time combined. Outside the black hole, your world line has choices. It can curve toward the black hole or away from it, depending on how you move. But once you cross the horizon, every possible world line, no matter its direction, points toward the singularity at the center. It is exactly as inevitable as time itself moving forward. You cannot choose to move toward tomorrow more slowly, or refuse to arrive at next Thursday. Inside a black hole, moving toward the center becomes exactly that inevitable and exactly that inescapable. And this is perhaps the most quietly terrifying realization of this entire fall. It isn't a battle you lose. It isn't a struggle against overwhelming force. It's simply the geometry of space rearranging itself so completely that struggle becomes meaningless. There is no direction to fight toward. There is no version of resistance that changes the outcome. The center isn't pulling you like a rope pulls a swimmer against a current. The center has become the only future that exists for you, in the same absolute sense that tomorrow is the only future that exists for all of us right now, in this ordinary, unremarkable moment. But silence, we should be clear, does not mean nothing is happening to your body. Because while the crossing itself might pass unnoticed, gravity around you has already begun behaving unevenly, pulling harder on the parts of you closer to the center than on the parts farther away. And that difference, subtle at first, faint enough to ignore in these opening moments, is about to become the defining feature of everything that follows. What began as calm, weightless falling is about to become something the human body was never built to withstand. That unevenness we mentioned has a name, and once you understand it, you'll never think of gravity the same way again. Scientists call it a tidal force, not a mysterious new kind of physics, but the same force that shapes ocean tides here on Earth, simply magnified to an unimaginable degree. And near a black hole, this small familiar effect becomes the first true physical danger of the entire fall. Here's the basic idea, and it's simpler than it sounds. Gravity grows weaker with distance. That's true everywhere, always. It means that if your feet are closer to a black hole than your head, your feet feel a slightly stronger pull than your head does. On Earth, this difference is so small across the length of your body that you'd never notice it in a lifetime. The Earth's gravity is gentle, and its pull barely changes at all across a distance of, say, 2 meters. But black holes are not gentle, and the closer you get to one, the more dramatically gravity changes over even the shortest distances. Think of it this way. Imagine holding a rubber band between your 2 hands, and someone begins pulling one end far more forcefully than the other. At first, you'd barely notice the difference, but the harder the pull becomes, and the more unevenly it's applied, the more that rubber band would begin to stretch, thinning out in the middle, elongating in the direction of the pull. Your body, falling feet first toward a black hole, becomes exactly that rubber band, except the hands pulling on it aren't hands at all. They're gravity itself, growing violently stronger with every kilometer you descend. For a black hole formed from a collapsed star, one holding perhaps 10 times the mass of our Sun, this stretching becomes catastrophic long before you ever reach the event horizon. Because these black holes are small, their gravity changes with brutal sharpness over very short distances. Physicists have calculated that for a black hole like this, tidal forces would become fatal from thousands of kilometers away, long before the boundary itself. Your body would begin to elongate, gently at first, then unmistakably, the space between your head and feet no longer feeling like a single unified object. But here's the detail that makes this entire story so much stranger, so much more layered than most people realize. Not all black holes behave this way. The size of a black hole changes everything about how brutal or how gentle this stretching feels. A stellar black hole, small and dense, creates gravity that changes ferociously over short distances, precisely because all that mass is compressed into a space only a few tens of kilometers wide. But a supermassive black hole, the kind sitting at the center of galaxies, holding the mass of millions or billions of suns, spreads that same mass across an event horizon that might stretch for millions, even billions of miles. And strange as it sounds, that vastness actually softens the pull. Because the event horizon is so enormous, the difference in gravity between where your head is and where your feet are becomes almost negligible, even as you approach and cross the boundary itself. This is one of the quiet, unsettling truths of black hole physics that rarely gets mentioned. The larger and more terrifying a black hole sounds, in terms of raw mass, the gentler its immediate touch might actually be. Size, in this case, doesn't mean more violence. It means a longer, calmer descent before anything catastrophic begins. This is why the black hole you're falling toward matters enormously to how this story unfolds. A stellar mass black hole would tear a human body apart long before reaching the horizon, the stretching becoming unbearable at a safe mathematical distance outside the point of no return. But a supermassive black hole, particularly one on the scale of galactic centers, might allow you to cross the horizon itself while your body remains completely, deceptively intact. The tearing would still come. It always comes eventually, but the timeline, the pacing of this particular horror depends entirely on scale. Think about the strange asymmetry in that. The event horizon we described earlier is silent, invisible, undetectable by any local measurement, regardless of the black hole's size. But the stretching, the actual physical danger, depends completely on how large that black hole happens to be. Two entirely different kinds of black holes, two entirely different experiences of the exact same fall. One ends in destruction long before the point of no return. The other allows you to cross that boundary whole, still yourself, still recognizably human, carrying the stretching forward into a darkness from which nothing can now escape. And this raises an uncomfortable question worth sitting with as we continue. If the stretching hasn't become unbearable yet, if your body remains intact even as gravity begins to pull unevenly across your length, what happens as that unevenness continues to grow, uninterrupted with no floor beneath you to stop the fall? Because tidal forces don't plateau. They don't level off politely at some tolerable maximum. They continue increasing gradually and then catastrophically the closer you draw toward the center of everything. For now, simply notice the sensation, faint but unmistakable, of something in your body beginning to feel subtly wrong. A pull in your ankles slightly stronger than the pull in your shoulders. A quiet, physical wrongness that will only intensify from here. Because what began as an almost imperceptible difference in gravity is about to become the defining, transformative force of this entire descent. That wrongness in your body has a name now, one that sounds almost playful for something so extreme. Physicists call this process spaghettification. It's a strange, almost gentle word for a process that ends in complete destruction. But the image it conjures is exactly right. And understanding that image will help you understand everything that follows. Picture a strand of raw spaghetti, straight and rigid, held between two hands. Now imagine one hand pulling away slowly, steadily, while the other stays fixed. At first, nothing happens. The strand simply stretches, almost imperceptibly, the way any solid object resists a small amount of tension. But keep pulling, and the strand begins to thin. Not break, not yet. Just thin, elongating along its length as the material stretches beyond its natural shape. Your body, falling feet first toward the center of a black hole, is undergoing exactly this same transformation, except the hands pulling on you are gravity itself, and they never stop tightening. Here's the thing most people don't realize about this process. It doesn't happen all at once. It isn't a single, violent snap. It's gradual, progressive, layered, the same way a rubber band doesn't shatter the instant you pull it, but stretches, thins, and only eventually tears once the tension exceeds what the material can bear. Your feet, closer to the black hole's center, would be pulled with slightly more force than your knees. Your knees pulled slightly more than your waist more than your chest. Every part of you stretched at a slightly different rate until your entire body becomes less like a person and more like a long, thin thread extended toward the darkness ahead. And this stretching isn't limited to just the vertical length of your body. Something equally strange happens sideways. As you fall, gravity doesn't just pull your head and feet apart. It also compresses you from the sides, squeezing your shoulders and hips inward, toward the central line of your fall. Picture squeezing a lump of dough from both sides, while simultaneously pulling it lengthwise from the top and bottom. It stretches long and thin in one direction, while it's compressed and narrowed in the other. This is the true geometry of spaghettification: elongation in one direction, compression in the other, occurring simultaneously, continuously, without pause. For a black hole formed from a collapsed star, this process would unfold with shocking speed. Calculations suggest that stretching strong enough to be fatal could occur in a matter of seconds, the tension building from barely noticeable to catastrophic faster than the human nervous system could even process the pain. Your body would be pulled apart at the cellular level, individual cells stretched and torn before you ever had time to fully comprehend what was happening. A brutal, rapid, almost merciful shortness to it, if there's any mercy at all in a death like this. But remember what we discussed about scale. Around a supermassive black hole, one holding the mass of millions of suns, this same process would unfold with an entirely different rhythm. Instead of seconds, the stretching might take hours. Instead of a sudden catastrophic tearing, a slow, almost meditative elongation, subtle enough at first that you might not even register it as danger. Your body drawn longer and thinner by degrees, minute by minute, the transformation so gradual that the earliest stages might feel like nothing more than an unusual pulling sensation, easy to dismiss, easy to ignore. Here's the detail that makes this genuinely unsettling rather than simply painful. Around the largest black holes known to exist, the ones spanning billions of miles across, some physicists have calculated that spaghettification might not become fatal until you are already deep inside the event horizon itself, which means, in theory, you could cross the single most irreversible boundary in the universe, still whole, still yourself, and continue falling for what might feel like a significant stretch of time before the stretching finally overtakes you, trapped forever, past the point of no return, yet not instantly destroyed, simply falling deeper and deeper toward an outcome that has already become inevitable but has not yet arrived. Think about how strange that timeline actually is. The boundary that traps you forever and the moment that finally kills you are not the same event at all. They might be separated by minutes, around the largest black holes, potentially longer. An extended stretch of existence alone, falling through absolute darkness, already beyond any possibility of rescue, and yet still alive, still thinking, still aware, waiting for a fate that has already been sealed but has not yet been delivered. We should be clear about something here, because it matters. Nothing has ever actually fallen into a black hole and reported back what this feels like. Everything we're describing comes from the equations of general relativity, tested rigorously in countless other contexts, applied here to a scenario no human being has ever survived to describe firsthand. It is, in every sense, an educated extrapolation, drawn from mathematics that has proven remarkably reliable everywhere else scientists have tested it. And this raises the question that will guide us through much of what remains tonight. If the stretching itself might not be instantaneous, if there is time, real time, stretched out between crossing the horizon and reaching the point of total destruction, what happens to your perception of that time? Because gravity, as it turns out, doesn't just bend space and pull unevenly on bodies, it bends time itself. And the closer you fall toward the center of a black hole, the stranger your relationship with time becomes, both for you and for everyone you've left behind. So let's leave your falling body for a moment and turn our attention to someone else, someone watching from far away, a friend perhaps, safely aboard a distant ship, telescope trained on you as you continue your descent. Because what that friend sees and what you experience are about to become two completely different stories, unfolding from the exact same fall. This effect is called gravitational time dilation, and it's one of the most well-tested predictions in all of physics. Here's the basic idea. Gravity doesn't just bend space, it bends time. And the stronger the gravity, the slower time passes, relative to someone farther away in weaker gravity. This isn't philosophy. It isn't a strange thought experiment confined to chalkboards. Satellites orbiting Earth right now experience time slightly differently than clocks on the ground. A difference so precise that GPS systems must correct for it constantly, or your phone's map would drift off course within minutes. Now scale that same effect up to something as extreme as a black hole. As you fall closer to the event horizon, time, from your friend's perspective, watching from a distance, appears to slow down. Not slightly, not subtly, dramatically. The closer you get to that boundary, the more sluggish your movements would appear through the telescope. Your fall, which feels continuous and steady to you, would look to your friend like a film gradually slowing toward a frozen frame, each second stretching longer than the last. Here's the thing most people don't realize about this slowing. It never actually appears to finish. Mathematically, according to the equations of general relativity, an outside observer would never actually see you cross the event horizon, not because you don't cross it, you do from your own perspective, in your own experience of time, but because the light carrying the image of you crossing that boundary takes longer and longer to escape the black hole's gravity, stretched thinner and redder with each passing moment, approaching the horizon asymptotically without ever quite completing the picture. Think about how strange that actually is. From your friend's viewpoint, you would appear to freeze, forever, at the very edge of the boundary. Not because time has stopped for you, but because the information showing your final approach takes an infinite amount of outside time to fully arrive. Your image would grow dimmer and dimmer, the light stretching into longer and longer wavelengths, shifting from white to red, to eventually becoming too faint to detect at all. You wouldn't vanish in an instant. You would fade slowly into a silence indistinguishable from nothing. And here's the detail that makes this genuinely disorienting, worth sitting with quietly for a moment. While your friend watches you seem to freeze forever at the boundary, you, in your own experience, would feel nothing of the sort. From your perspective, time continues normally. Your heartbeat doesn't slow. Your thoughts don't stretch into eternity. You cross the horizon in what feels, to you, like an entirely ordinary passage of seconds or minutes, continuing your fall exactly as before. Two completely different timelines, two completely different truths, both scientifically accurate, both happening simultaneously, depending entirely on where you happen to be standing. This isn't a flaw in the theory, it's one of its most profound features. Time, according to general relativity, was never the single, universal current we intuitively imagine it to be. It was always relative, always dependent on gravity, always something that flows differently depending on where you're standing and how strong the pull around you happens to be. A black hole simply takes this ordinary, everyday truth, the same truth that requires tiny corrections for satellites overhead, and stretches it to its absolute, almost unimaginable extreme. Consider too what this means for anything falling in ahead of you. Matter, dust, the light of long collapsed stars, anything that has ever approached a black hole's boundary throughout its entire existence. From an outside perspective, none of it has technically finished falling in yet. Every single object that has ever approached an event horizon remains, in some sense, frozen at that boundary forever. An infinite queue of stretched, reddened, fading images, layered one atop another, each one approaching but never quite arriving, at least not from where we stand watching. And yet, we know black holes grow. We know they consume matter, gain mass, merge with one another in cataclysmic collisions detected as ripples in space itself. So clearly, from some perspective, things do finish falling in. It's simply not our perspective, watching safely from a distance. It is only ever the perspective of the thing that fell, the perspective that experiences its own time moving forward, uninterrupted, all the way to whatever waits at the centre. This divide between what an outside observer sees and what you yourself would experience is about to matter enormously for the rest of this story. Because it means the black hole you're approaching looks like two entirely different objects, depending on who's asking. To your friend watching from safety, you become a fading, frozen image, forever suspended at an unreachable boundary. But to you, falling ever closer, time continues, uninterrupted, carrying you steadily towards something that, from the inside, feels disturbingly, undeniably real. Let's stay with your friend a little longer, telescope still trained on the point of light that used to be you, because there's something worth understanding more deeply here, something that goes beyond simply knowing that time slows down. What exactly would they actually see, moment by moment, as that final image stretches toward its unreachable ending? Light, when it climbs out of a gravitational well, loses energy in the process. Think of it like a ball thrown upward, slowing as it climbs against gravity's pull. Light can't slow down, of course. It always travels at the same speed. So instead, it loses energy differently. It stretches. Its wavelength grows longer, shifting steadily from blue toward red, and eventually beyond red entirely, into wavelengths the human eye was never built to see. Astronomers call this gravitational redshift, and near a black hole, it becomes so extreme that it changes the entire character of what's being observed. Here's the thing most people don't realize about this stretching. It isn't gradual and gentle the whole way down. In the earliest part of your fall, the redshift would be barely noticeable, a faint warming of colour, easy to miss entirely. But as you approach the horizon, the stretching accelerates dramatically, compressing an enormous change into the final moments before that frozen, fading image forms. Your friend wouldn't watch a slow, even dimming spread evenly across hours. They would watch something closer to ordinary, then suddenly rapidly, a final flicker of deep red light, stretching longer and fainter within what feels, to them, like a remarkably short span of time, before the signal grows too weak to register at all. And this is where the old name for these objects becomes suddenly relevant again. Before the term black hole existed, scientists sometimes called them frozen stars, precisely because of this effect. From the outside, a collapsing star never appeared to fully finish collapsing. Its surface seemed to hover, forever approaching, but never quite reaching the point where its own gravity would seal it away completely. The name fell out of favour decades ago, replaced by something more evocative of the darkness itself. But the underlying physics it described was never wrong. It was, in some sense, more literally accurate than the name that replaced it. Think about what your friend is left with then. Not an event, not a clean, documented moment of you crossing the boundary. Just an ever fainter smear of red light, asymptotically approaching an edge it will never mathematically complete. If they kept their telescope trained on that exact point for years, decades, centuries, they would, in principle, still be receiving an infinitesimally faint trace of that final image, stretched almost beyond recognition, but never technically finished, never entirely gone. A last photograph that keeps being taken, forever, without ever being fully developed. Here's the part that turns this from strange physics into something genuinely unsettling to sit with. If your friend can never observe you actually crossing the horizon, does that mean, from the universe's outside perspective, you never actually do it? Physicists have wrestled with versions of this question for decades, and the honest answer is that it depends entirely on whose account of reality you're asking. From your own experience, falling forward through your own continuous time, the crossing happens decisively in what feels like an ordinary moment. From the perspective of anyone watching from outside, that same crossing recedes forever into an unreachable future, always approaching, never quite arriving. Physicists have a name for this apparent contradiction. They call it complementarity, the idea that both descriptions, yours and your friend's, are simultaneously fully true, without either one being the more real or more correct version of events. It isn't that one of you's mistaken. It isn't an illusion resolved once enough information comes in. Both timelines are treated mathematically as equally valid accounts of the same underlying event, viewed from two positions that can never be reconciled into a single shared story. No observer, in principle, could ever occupy both positions at once to compare notes. Think about how quietly disorienting that really is. Somewhere in this universe, right now, there may be points of light, faint, stretched, barely detectable, that represent the final visible traces of matter that fell into black holes millions, even billions of years ago. Frozen stars in the old language, still technically radiating their last visible moment, endlessly, into a universe that has long since moved on. Not ghosts, not illusions, simply the mathematics of gravity, refusing to let go of a single final image, forever. And for you, falling forward through your own uninterrupted time, none of this outside drama touches you at all. You do not feel yourself freezing. You do not experience your own image stretching into red light, dimming toward invisibility. That entire story belongs to the observer, not to you. Your story continues moment by moment, exactly as it always has, carrying you steadily closer to a boundary that, from where you stand, has never once shown any sign of hesitation. This is the paradox we're left holding as we continue. Two entirely different accounts of the same fall, both true, neither one lying, and no way to stand in both places long enough to reconcile them. And it's about to matter enormously, because the moment is almost here. The moment where your continuous, unhesitating experience finally meets that boundary your friend can never quite see you cross. So here we are, not your friend, watching from a comfortable distance, but you, continuing forward through your own uninterrupted time. The boundary we've been circling this entire journey, the one that stretches your friend's view of you into an endless, fading photograph, is no longer something ahead of you. It's here. And the most important thing to understand about this exact moment is how utterly unremarkable it would feel. There is no flash, no resistance, no line drawn across the darkness to mark where you are. If you were watching your instruments, nothing on them would spike, nothing would fail, nothing would announce, in any measurable way, that you have just left the observable universe permanently. The stars behind you, if you dared to look back, would still be visible, still recognizable, still arranged in roughly the patterns you remember. For a little while longer, everything would still look astonishingly, deceptively normal. Here's the thing most people don't realize about this moment. The single fact that makes the event horizon perhaps the strangest boundary conceivable. It has no local definition at all. You cannot measure your way to discovering it. There's no instrument, no sensor, no equation you could run using only information available at your exact location that would tell you decisively in that instant that you've crossed it. The event horizon is defined entirely by what happens globally, by whether escape is mathematically possible from where you are, not by anything you could detect happening directly around you. Think about how genuinely strange that is. Every other boundary you've ever crossed in your life gave you some kind of signal. A doorway has a frame. A cliff edge has a visible drop. Even the border between countries, invisible as it often is, gets marked by a sign, a fence, a checkpoint, something acknowledging the change. The event horizon offers none of this. It is defined purely by the future, by whether any possible path from this exact point could ever lead back outward again. And once that answer becomes no, the boundary has been crossed silently, invisibly, with absolutely nothing marking the transition in the present moment. This is why, if you tried to calculate your exact position relative to the horizon using only what you could observe around you, right now, in this instant, you simply couldn't do it. Some physicists have described this using an unsettling phrase. Nothing bad happens here. At least nothing you could point to, measure, or feel directly. distinguishing this specific location from the empty space you passed through minutes earlier. The badness, if we can call it that, exists only in the shape of your future, not in anything happening to your body in this present, immediate second. And yet everything has changed. Somewhere in this silence, without ceremony, every direction available to you has quietly rearranged itself. Forward has become the only direction that exists. Not because a wall now blocks the other paths, simply because space itself curves in such a way that outward no longer leads anywhere but further inward. It's the same eerie inevitability we described earlier, the same certainty with which today leads to tomorrow, except now it applies to your literal position in space, not merely to the passage of time. Here's a detail that deepens the strangeness even further. Because the horizon isn't a physical object, it isn't even perfectly fixed in place the way a wall would be. As matter falls into a black hole, as the black hole itself grows in mass, its event horizon actually expands outward to accommodate the new material. This means the exact boundary you crossed might, in some sense, have shifted slightly by the time you're asking the question, growing to absorb whatever continues falling in behind you. The edge of no return is not a static line drawn once and left unchanged. It's a boundary that breathes slowly with every new piece of matter the black hole consumes. Complete silence. No signal, no resistance. That was always the promise of this boundary, established from the very beginning of this journey. And here, finally, it delivers exactly what it promised. No dramatic transition, no final battle at the threshold. Simply a continuation, seamless and quiet, of a fall that began long ago, now carrying you into a region of space from which nothing, not light, not radio waves, not even the faintest whisper of information, could ever reach the universe you've left behind. And this is perhaps the most quietly terrifying truth of everything we've covered so far. You would not know with certainty in this exact moment that this is the moment. You might suspect it based on how long you've been falling, based on rough calculations of the black hole's size and your approach, but you could not verify it directly. Not from where you are, not with anything available to you locally. The most significant threshold a person could ever cross, and it offers no confirmation whatsoever that it has, in fact, been crossed. What lies ahead now is different from everything before it, not because the fall itself changes character immediately, but because you are no longer approaching darkness from the outside, wondering what it contains. You are now inside it, part of it, moving through a space cut off entirely from everything you've ever known. And what that darkness actually contains, what it feels like to exist within a region the rest of the universe can never observe again, is where we turn next. So this is what it means to be inside. Not inside a structure, not inside a container with walls you could reach out and touch. Inside a region of space that the rest of the universe can no longer observe, no longer reach, no longer influence in any way whatsoever. And the very first thing you would notice here, more than anything else, is the absence. A depth of absence that nothing on the outside could ever have prepared you for. No light reaches you from behind anymore, at least not in the way it once did. The stars you left behind, the faint glow of matter still swirling outside the horizon, all of it has fallen away, red-shifted into wavelengths beyond anything your eyes could register, or simply left behind entirely as you continue moving forward, deeper into the darkness ahead. What remains is not blackness in the ordinary sense, the kind you'd experience closing your eyes in a dark room, comforted by the knowledge that light still exists somewhere nearby. This is a darkness woven into the fabric of the space itself, a darkness that isn't merely an absence of illumination, but a fundamental property of the region you now occupy. Here's the thing most people don't realize about this silence. It isn't only visual, it's total in every sense that matters. No radio waves reach you from outside, and none of your own signals, if you try to send them, could ever reach anyone. listening beyond the horizon. Complete separation. Not distance in the way two ships might drift far apart while still capable, in principle, of eventually reconnecting. This is a severing, absolute and final, of any possible channel between where you are now and everything you have ever known. Think about how profound that isolation actually is. Throughout human history, no matter how remote the location, no matter how deep beneath the ocean or how far into space, some thread of connection has always technically remained possible. A signal, however faint, could always theoretically travel back. Here, that possibility doesn't merely become difficult. It becomes mathematically, permanently impossible. Not because the distance is too great, because the very geometry of space between you and everyone else now points in only one direction, and that direction leads only deeper inward, never back out. And yet, within this profound isolation, something else becomes strange, in an entirely unexpected way. Time itself, at least, the ordinary way we think about time, direction and space, start to blur together here in ways that are difficult to describe using everyday language. Outside a black hole, you can move freely through space, but time moves relentlessly forward whether you like it or not. Inside the horizon, physicists describe something remarkable. The roles begin to swap. Moving toward the singularity stops feeling like moving through space at all and starts to resemble something closer to the forward march of time itself, as inevitable and undeniable as the fact that this moment will inevitably become the next. Here's a way to hold that idea gently, without needing the full mathematics behind it. Imagine if outside you could choose to walk east, west, north, or south, freely, whenever you liked. But once you crossed a certain point, that freedom vanished, and you found yourself only ever able to move in one single direction, exactly the way you can only ever move forward through time, never backward, no matter how much you might wish otherwise. That's the strange transformation happening here. Inward has stopped being merely a direction in space. It has become something closer to the passage of time itself, moving forward, always forward, toward wherever it inevitably leads. This silence, this darkness, this collapse of ordinary directionality might sound purely frightening, and in many ways, it is. But there's also something almost meditative about it, something that belongs, oddly enough, to the same family of experience as staring up at a truly dark, star-filled sky, far from any city lights, feeling impossibly small beneath something impossibly vast. Except here, there is no sky left to look up at, no stars to anchor your sense of scale, just the profound, encompassing quiet of a space that has been completely, irrevocably cut off from everything else that exists. Almost everything is missing here. No sound, because sound requires a medium to travel through, and none exists in the vacuum of space regardless. No light, at least none arriving from outside. No signal, no connection, no thread leading back to anything familiar. Brutally isolated in the truest sense that word could ever be used. And yet, remarkably, you continue existing within it, continuing forward, carried by a trajectory that was set the moment you crossed that silent, invisible boundary behind you. We should pause here and acknowledge something important. This description, however carefully reasoned from the mathematics of general relativity, remains theoretical in every practical sense. No instrument has ever transmitted data from beyond an event horizon, and none ever could, given everything we've established about the nature of that boundary. Everything we're describing is drawn from equations that have proven extraordinarily reliable in every other context. Scientists have tested them, applied here to a region of the universe forever closed off from direct observation. And still, the equations insist that something specific, something structured, waits ahead in this darkness. Not endless empty space, stretching forever without form or feature. Something with actual mathematical properties, a destination that this entire journey has been steadily, inevitably approaching since the very first moment you began to fall. A place where the laws of physics themselves, the very equations we've relied on throughout this journey, finally, completely break down. Scientists call this destination the singularity, and it might be the strangest word in all of physics. Not because the concept itself is complicated, but because of what it actually admits. When physicists use this word, they are, in effect, confessing that their equations have stopped working entirely. Not become difficult, not become imprecise, stopped completely, the way a calculator might display an error message when asked to divide by 0. Here's the thing most people don't realize about the singularity. It isn't a place in the way we normally think of places, a location with a size, a shape, a surface you could touch or measure. According to the mathematics of general relativity, the singularity at the center of a black hole represents a point where density becomes infinite, where all the mass that ever fell in, every star, every scrap of dust, every fragment of matter gets compressed into a space with, technically, no volume at all. Infinite density, zero size, numbers that don't describe a physical object so much as reveal the exact location where our best theory of gravity simply gives up trying to describe anything at all. Think about how uncomfortable that admission actually is, coming from a science built almost entirely on precision. General relativity has been tested with extraordinary success for over a century now, predicting the bending of starlight around the Sun, the exact orbit of Mercury, the existence of gravitational waves detected rippling through space from collisions of black holes themselves. It works, remarkably, almost everywhere physicists have ever tested it. And yet, at the singularity, this same theory doesn't merely become less accurate, it stops making sense entirely, predicting infinities that no physicist believes represent anything physically real. Here's what most researchers actually suspect is happening, even though nobody can currently prove it. The singularity predicted by general relativity likely isn't the true, final answer. It's more probably a signal, a mathematical alarm bell, indicating that another set of rules, ones we don't yet fully understand, must take over before you ever actually reach infinite density. Physicists suspect those missing rules belong to quantum mechanics, the physics governing the impossibly small, the physics that has never yet been successfully merged with the physics of gravity into a single, unified theory. Somewhere in that gap, in that unfinished merger between two of humanity's greatest scientific achievements, the true nature of the singularity waits unknown. And this is genuinely one of the most shocking truths in all of modern physics, one that rarely gets emphasized enough outside of academic circles. We do not know what exists at the center of a black hole, not vaguely, not approximately. We have built spacecraft that photograph the rings of distant planets and satellites that detect ripples in space itself from collisions occurring billions of light years away, and telescopes that captured the actual image of a black hole's shadow. And yet, the single most extreme environment predicted by our own equations remains, fundamentally, a mystery we cannot currently solve. Some physicists propose that quantum effects prevent matter from ever truly collapsing to zero size, suggesting instead an unimaginably dense but finite core, something scientists sometimes call a Planck star, referencing the smallest meaningful unit of length in physics. Others propose more radical alternatives entirely, structures that avoid a true singularity altogether, replacing it with exotic states of matter or geometry that current theories can only partially describe. None of these ideas have been confirmed. None of them can be tested directly, given everything we've already established about the impossibility of retrieving information from beyond an event horizon. Think about the strange position this puts us in, as curious, searching creatures trying to understand our own universe. We can calculate, with impressive precision, everything that happens up until this exact point. The stretching, the silence, the bending of light and time, but the actual destination, the place this entire journey has been leading toward from the very beginning, remains genuinely unknown, hidden not by lack of effort, but by the fundamental limits of what can ever be observed or tested from outside. Here's the thing that makes this feel less like an ending, though, and more like an invitation. Throughout history, whenever physics has encountered a genuine wall like this one, a place where equations break down and predict impossible infinities, it has often signaled the doorway to an entirely new understanding waiting just beyond. This happened before, when physicists first confronted infinities in other calculations, only to discover deeper theories that resolved them elegantly, revealing entirely new layers of how the universe actually works. Many physicists believe the singularity represents exactly this kind of doorway, not a true dead end, but a boundary marking the edge of our current understanding, waiting for whatever theory finally unites gravity and quantum mechanics into a single, coherent picture. And so, in some sense, falling toward this final point means falling toward the very edge of human knowledge itself. Not merely the edge of your own personal journey, but the edge of what science can currently explain about the universe you exist within. Somewhere ahead, mathematically, waits a place where the rules run out. What actually happens there, physically, remains one of the last great unanswered questions in modern physics. A mystery hidden behind a boundary that guarantees by its very nature that no one will ever bring back an answer. Let's step back now, just for a moment, from that unknown point at the centre and reconsider the entire journey through a different lens. Because everything we've described so far, the stretching, the silence, the bending of light and time, doesn't unfold the same way in every black hole. Size changes everything. And to really understand the brutal range of experiences hidden inside that single word, black hole, we need to talk about scale. We touched on this earlier, but it's worth sitting with the true scope of it now. A stellar black hole, born from the collapse of a massive star, typically holds somewhere between 5 and 20 times the mass of our Sun, compressed into a region only a few tens of kilometers across. Small by cosmic standards, but ferociously dense. Gravity near a black hole like this changes so sharply over short distances that spaghettification becomes fatal long before you ever reach the event horizon itself. A quick, brutal, almost merciless end, measured in mere seconds. But supermassive black holes exist on a completely different scale of reality altogether. These giants sit at the centers of nearly every large galaxy, including our own, holding masses ranging from millions to billions of times that of the Sun. Sagittarius A star, the supermassive black hole anchoring the center of the Milky Way, contains roughly 4 million solar masses, compressed into a region smaller than the orbit of Mercury around our Sun. And even that almost unthinkable number pales beside the largest known supermassive black holes, some holding tens of billions of solar masses, their event horizons stretching wider than our entire solar system. Here's the thing most people don't realize about this difference in scale. Bigger doesn't mean more violent, at least not in the way intuition suggests. Because a supermassive black hole spreads its enormous mass across an event horizon so vast, sometimes billions of miles across, the change in gravity between your head and your feet, even right at the boundary, becomes remarkably gentle. Tidal forces that would tear you apart instantly near a stellar black hole might remain survivable for hours, even days, near the largest supermassive giants known to exist. Think about what that actually means for the shape of this entire journey. Near a small stellar mass black hole, everything we described happens in a horrifying rush, compressed into moments. The stretching, the crossing, the destruction, all collapsed into a handful of seconds, almost too fast for a human mind to fully process before it ends. But near a supermassive giant, that same sequence of events stretches out, patiently, almost gently, across a timeline a person could actually live through, think through, and endure, at least for a while. And this creates a strange, almost paradoxical possibility worth pausing on. You could, in theory, fall through the event horizon of a sufficiently large, supermassive black hole, cross that most irreversible boundary in the entire universe, and for a time remain completely intact, whole, alive, conscious, continuing to fall through absolute darkness, cut off entirely from everything you've ever known, and yet still yourself, for what might feel like a genuinely significant stretch of time, before the stretching finally, inevitably, catches up with you. Here's a number worth sitting with to really appreciate the scale we're talking about. The event horizon of the largest known supermassive black holes could swallow our entire solar system, Sun, Earth, every planet, and still have room to spare, stretching outward across a boundary many billions of miles in diameter. Falling toward the center of something this large isn't like falling toward a small dense object at all. It's closer to falling through an entire region of space, vast enough that the destination itself feels less like a target and more like an entire landscape, waiting quietly in the dark. And yet, however gentle the initial crossing might feel, however patient the descent through that early darkness, the outcome never actually changes. Every path still leads inward. Every direction still collapses toward that same unknown point, the singularity, waiting at the center, regardless of how vast or how modest the black hole happens to be. Scale changes the pacing of this story. It changes how much time you're given to notice, to think, to feel the weight of what's happening around you, but it never changes the ending itself. This is perhaps one of the more quietly unsettling truths of everything we've covered tonight. The larger, more massive, more genuinely terrifying sounding a black hole becomes, in terms of raw scale, the gentler and more prolonged its actual touch might be. Violence in this particular corner of the universe doesn't scale the way we instinctively expect. Sometimes, the largest, most overwhelming force imaginable arrives not as a sudden shock, but as an unbearably patient, almost peaceful unfolding, stretched across hours instead of seconds. And this brings us quite naturally to the supermassive giant closest to home, the one anchoring our own galaxy, sitting quietly at its center, roughly 26,000 light-years from where you're likely lying right now, listening to this in the dark. What would it actually mean to approach that particular black hole? Not a hypothetical giant somewhere in the distant universe, but the one our entire galaxy, our sun, our planet, and everything you've ever known has been quietly orbiting around for the whole of its existence. Its name is Sagittarius A star, and for most of human history, we didn't even know it existed. Hidden behind thick clouds of dust and gas at the very center of our galaxy, invisible to ordinary telescopes, it took decades of patient observation, tracking the orbits of stars swinging impossibly close to something unseen, before astronomers could finally confirm what was hiding there. A supermassive black hole, quietly anchoring the gravitational center of everything you've ever known. Here's the scale worth sitting with. Sagittarius. A star contains roughly 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. 26,000 light-years separate it from where you're lying right now, a distance so vast that even light, travelling at its impossible speed, needs 26,000 years just to cross the gap. And yet, despite that staggering distance, its gravity reaches across the entire galaxy, quietly governing the slow, patient orbits of hundreds of billions of stars, our own sun included, all of them circling this hidden centre like planets around a sun we cannot see. In 2022, astronomers finally captured a direct image of it, using that same global network of telescopes that had photographed the black hole in M87 years earlier. The results showed the same unmistakable signature, a dark, perfectly circular shadow, ringed by the glow of superheated matter, bent and distorted by gravity into a golden halo. Here's the thing most people don't realize about that achievement. Sagittarius A star's event horizon is actually smaller than M87's, but because it's so much closer to us, the two appear nearly identical in size from Earth. A strange coincidence of cosmic geometry that made capturing both images possible using the very same technique. Now imagine actually approaching it, not observing from a telescope 26,000 light years away, but drawing close, the way we've been imagining this entire fall. Because Sagittarius A star sits comfortably in that supermassive category we just described, its enormous mass spread across a correspondingly vast event horizon, the tidal forces near its boundary would remain remarkably gentle. You could, in principle, cross its horizon without being torn apart in that instant. The stretching would come, eventually, inevitably, but not immediately. Not with the brutal, instant violence of a smaller stellar black hole. Think about what that means, practically, for anything drawn toward it. Gas and dust spiraling into Sagittarius. A star don't simply vanish in an instant, torn apart the moment they approach. They form vast, swirling disks, heated by friction and compression to millions of degrees, glowing brightly in X-ray and radio wavelengths, long before they ever reach the boundary itself. Astronomers have actually observed flares of light erupting from just outside its horizon, brief flashes thought to be caused by clumps of hot gas completing final orbits, moments before slipping past the point of no return. A quiet cosmic drama playing out at the very center of our galaxy, entirely invisible to the naked eye. Here's a detail that deepens the strangeness of our relationship with this hidden giant. Every star you've ever seen in the night sky, every constellation you've traced with your eyes since childhood, exists in orbit around this same invisible point. Our Sun completes one full orbit around Sagittarius, a star, roughly every 230 million years. A journey so long that the last time our solar system completed a full circuit, dinosaurs hadn't yet appeared on Earth. We are right now, at this very moment, quietly falling around a supermassive black hole, and we always have been, for the entire history of our solar system's existence. And yet, despite that intimate ancient relationship, despite orbiting this hidden giant since before life itself existed on our planet, we remain remarkably safe from it. 26,000 light-years is an almost incomprehensible buffer of distance, more than enough to keep its gravity gentle and diffuse by the time it reaches us, felt only as the slow, graceful curve of our galaxy's rotation. Nothing more dramatic than that. The same object capable of stretching a falling body into an unrecognizable thread, from this distance, simply keeps our entire galaxy gently, imperceptibly turning. Here's the shocking truth most people don't realize about our own cosmic address. We live our entire lives, birth to death, orbiting a black hole so massive it could swallow 4 million suns, and most of us never once think about it, never once look up and consider that the quiet, star-filled sky above hides at its very center an object capable of everything we've described tonight. It doesn't announce itself. It doesn't demand attention. It simply sits there, patiently, at the gravitational heart of everything, doing exactly what it has done for billions of years and will likely continue doing for billions more. And this brings us to something genuinely unexpected, a detail that upends almost everything most people assume about what falling into a black hole would actually feel like. Because if a supermassive giant like Sagittarius A star allows for a gentle crossing, a patient, almost peaceful descent rather than instant violence, then the true horror of this journey isn't what we've been led to imagine at all. It isn't a sudden, dramatic death at the boundary. It's something else entirely, something quieter, something that rarely gets mentioned, even among those who study these objects closely. Here it is then. The truth we've been quietly building toward this entire journey, one that rarely gets mentioned in the popular imagination of what a black hole actually does. Most people picture falling into one as an act of instant, spectacular violence, a crushing, a tearing, something swift and unmistakably brutal, over before the mind can even register what's happening. And for certain black holes, the small dense stellar ones, that picture is largely accurate. But for the largest black holes in the universe, the supermassive giants, like the one anchoring our own galaxy, that picture is almost entirely wrong. The real horror for these giants isn't speed, it's patience. It's the possibility of crossing the single, most irreversible boundary in existence and continuing to exist afterward, aware, intact, thinking, for what might stretch into hours. Not because anything has gone wrong with the physics, because this is exactly what the mathematics predicts, calmly and consistently, for anything falling into an object large enough. The most extreme environment in the known universe and the immediate experience of entering it might feel disturbingly, unsettlingly ordinary. Here's the thing most people don't realize about this delay. It isn't a mercy, it isn't a gentler version of the same ending, softened somehow by the extra time. It's arguably crueler in its own quiet way, because that extra time isn't spent doing anything. There's no escape route to search for, no rescue that becomes possible, no version of events where those additional hours change the outcome in any way whatsoever. The ending has already been sealed the moment you cross the horizon behind you. What remains is simply the waiting. Conscious, aware, alone, drifting through absolute darkness toward a fate that has already been decided. Think about what that would actually mean, moment to moment. No stars behind you anymore, nothing to look back on. No possibility of turning around, of course. We've established that clearly by now. But also, crucially, no way to know exactly how much time remains, no clock counting down, no landmark passing by to measure your progress against. Just the quiet, steady continuation of a fall that began long ago, deeper into a silence with no reference points at all, waiting for stretching that has not yet arrived, but that, with absolute mathematical certainty, is still coming. And here's a detail that makes this even stranger, worth sitting with carefully. Some physicists have pointed out that during this extended period, falling through the region just inside a supermassive black hole's horizon, you would still, in principle, be capable of ordinary thought, reflection, memory, the full weight of everything you've ever experienced, still available to you, still running through your mind, uninterrupted by the darkness surrounding you. Not a swift unconsciousness, not a merciful blankness settling in immediately, simply continued awareness, drifting through absolute isolation for a length of time that would feel, to you, disturbingly substantial. Here's the shocking part, the piece of this puzzle that rarely gets emphasized outside of academic papers on the subject. This means the true danger of a black hole was never really about the crossing itself. The event horizon, so often treated as the dramatic, defining moment of destruction in popular imagination, isn't actually where the violence happens, at least not for these largest giants. It's simply a marker, a point of no return, entirely separate from the moment of actual physical destruction that follows later, deeper inside, closer to that unknown singularity we still don't fully understand. Think about how this reframes everything we've covered tonight. The stretching, the silence, the bending of light and time, all of it building not toward a single, unified moment of catastrophe, but toward two entirely separate events, spaced apart by an unknown and possibly significant stretch of continued existence. Crossing the horizon and finally reaching your end are not the same experience at all. They might be separated by minutes, for the largest black holes known to exist, potentially longer still. And this raises a question worth holding gently, without rushing to answer it. If awareness continues, if thought and memory remain intact for a stretch of time, inside that absolute darkness, what fills that time? Not action, since none is possible. Not escape, since none exists. perhaps only reflection, perhaps only the quiet, unhurried process of simply being alone inside a place cut off entirely from everything you've ever known, carried forward by a fall that started long before, and will finish whenever the equations finally, inevitably, catch up. This is, in many ways, the most quietly unsettling truth this entire journey has revealed. Not that black holes are violent, we already knew that, but that the violence and the crossing are not the same moment, and the space between them might be filled with nothing but stillness, and awareness, and time, stretching out in a darkness, with absolutely nothing left to measure it against. And it's this very stillness, this unexpected pocket of continued existence inside the darkness, that leads us toward one final strange twist in this story. Because even here, in a place forever cut off from the rest of the universe, physics insists that something is still happening. Something slow, something almost impossibly patient, something that connects even the darkest, most isolated object in existence back to the rest of the cosmos, in a way that took decades for scientists to even begin to understand. In the 1970s, a young physicist named Stephen Hawking turned his attention to a question that seemed almost absurd at the time. What happens when you combine the physics of black holes with the physics of the impossibly small, the strange probabilistic world of quantum mechanics? Nobody expected the answer he found, because according to his calculations, black holes are not perfectly, permanently black after all. They leak. Slowly, faintly, but unmistakably, they leak. Here's the idea, gently. Empty space, according to quantum mechanics, isn't truly empty at all. Even in a perfect vacuum, pairs of particles are constantly, briefly, popping into existence, one particle and its opposite, before annihilating each other and vanishing again, almost instantly, far too quickly to ever be directly observed under ordinary circumstances. This happens everywhere in the universe, constantly, an invisible, ceaseless flickering woven into the very fabric of space itself. Near the event horizon of a black hole, though, something strange interrupts this ordinary process, something that changes everything. Occasionally, one of these fleeting particle pairs forms right at the boundary, one particle on each side of the horizon. And because nothing can cross that boundary going outward, the particle on the inside falls into the black hole, while the particle on the outside escapes, unable to reunite with its partner and vanish as it normally would. From a distance, this escaping particle looks exactly like radiation, energy leaking outward from the black hole itself. Hawking's insight was to realize that this steady, faint leak wasn't just a mathematical curiosity. It represented something genuinely happening to the black hole itself. Here's the thing most people don't realize about this discovery. Every time one of these particles escapes, the black hole loses a tiny, almost immeasurably small amount of mass and energy. Over time, an incomprehensibly long time, this slow leak means the black hole is actually shrinking, evaporating, ever so gradually, back into ordinary radiation, spreading harmlessly out into the universe. The darkest, most inescapable object ever discovered isn't permanent after all. It's dying, slowly, whispering itself away, one impossibly faint particle at a time. But before this becomes something to worry about, let's be honest about the timescale involved, because it's almost impossible to overstate. For a black hole with the mass of our Sun, this evaporation process would take roughly 10 to the power of 67 years, a number so large it dwarfs the current age of our entire universe, which stands at only 13.8 billion years. For a supermassive black hole like Sagittarius A star, the timescale grows even more absurd, stretching toward 10 to the power of 90 years, or beyond. These are not numbers meant to be visualized. They exist simply to communicate one clear idea. On any timescale that matters to us, black holes are, for all practical purposes, eternal. And yet this discovery changed everything about how physicists understand these objects. Because it means black holes are not truly separate from the rest of the universe, sealed away forever behind their event horizons. They participate, however faintly, in the ongoing story of the cosmos, radiating energy back outward, connected in the smallest possible way to everything beyond their boundary, the most isolated objects imaginable, and even they cannot fully escape the universe's habit of eventually, inevitably, changing. Think about the strange poetry hidden in this discovery. A black hole spends its existence consuming everything that falls too close: matter, light, entire stars, pulling all of it into permanent, inescapable silence. And yet, across timescales that dwarf the age of the universe itself, that same black hole is slowly giving something back, whispering faint traces of energy outward, until eventually, impossibly far in the future, nothing remains of it at all. Consumption and eventual release, playing out across a timeline almost too vast for the human mind to properly hold. Here's a detail that adds another unsettling layer to this slow process. As a black hole shrinks through evaporation, it doesn't do so at a constant pace. The smaller it becomes, the faster the evaporation accelerates until, in its theoretical final moments, the process ends. Not gently, but in a sudden dramatic burst of radiation and energy. A quiet, patient death across almost inconceivable timescales, ending finally, not in silence, but in one last, brilliant flash, releasing whatever remains back into the universe all at once. And so even the darkest, most feared object in the cosmos, the very thing this entire journey has explored, turns out to be temporary. Not on any timescale relevant to us tonight, or to human civilization, or even to the entire history of life on Earth, but temporary nonetheless, in the truest, deepest sense that physics allows. Nothing, it seems, not even a black hole, truly escapes the universe's quiet, patient tendency toward change. And this discovery, remarkable as it is, opened the door to another question entirely, one physicists are still struggling to answer today. If a black hole eventually evaporates completely, disappearing back into radiation, what happens to everything it ever swallowed? Every star, every fragment of matter, every scrap of information about everything that ever fell inside. Does it simply vanish forever? Or does it, somehow, come back? This question, what happens to everything a black hole ever swallowed once it finally evaporates, turns out to be one of the deepest, most stubborn problems in modern physics. Scientists call it the information paradox, and it has divided some of the brightest minds in the field for decades, including Hawking himself, who spent much of his later career wrestling with the implications of his own earlier discovery. Here's the conflict at the heart of it, explained gently. Quantum mechanics, the physics governing the smallest scales of the universe, insists on something called information conservation. In simple terms, it says that the complete details of anything, its exact structure, its full history, can never be truly destroyed. It might be scrambled beyond recognition, rearranged into something unrecognizable, but never under any circumstances erased from the universe entirely. Everything that ever happens leaves a permanent, recoverable trace, even if that trace becomes impossibly difficult to read. But here's where black holes create a genuine problem. If something falls into a black hole, carrying with it all the information about what it was, its structure, its history, everything that made it uniquely itself, and that black hole eventually evaporates completely into featureless radiation, then that information appears to vanish along with it. Hawking radiation, as originally calculated, seemed to come out random, carrying no trace whatsoever of what had fallen in to create it, which means, according to the original math, information really could be destroyed permanently, contradicting one of the most fundamental principles in all of quantum physics. Think about why this bothered physicists so deeply, more than it might seem to on the surface. This wasn't merely an abstract technicality, it represented a genuine, direct contradiction between two of humanity's most successful physical theories. General relativity, governing gravity, and the large-scale structure of the universe seemed to demand that information could be lost forever inside a black hole. Quantum mechanics, governing the smallest scales of reality, insisted this was fundamentally, mathematically, impossible. Two theories, both extraordinarily well tested, both essential to modern physics, flatly disagreeing about what happens to information at the most extreme boundary either of them describes. Here's the thing most people don't realize about where this debate currently stands. It has never been fully resolved, even after decades of intense theoretical work by some of the most capable physicists alive. Various proposed solutions have emerged over the years, each attempting to reconcile this contradiction in different ways. Some suggest that information gradually leaks out, encoded within the Hawking radiation itself, in ways too subtle for the original calculations to capture. Others propose that information might be preserved on the event horizon itself, somehow imprinted on that boundary before anything actually falls through it. Still others suggest more radical restructurings of our understanding of space, time, and information altogether. One particularly striking idea, developed over the past couple of decades, suggests something called the holographic principle, proposing that all the information about everything that ever fell into a black hole might actually be encoded on the surface of its event horizon itself, like an image somehow painted across that entire boundary. If true, this would mean the three-dimensional experience of falling inward that we've described this entire journey might, in some deeper mathematical sense, be equivalent to information simply being recorded flat across a two-dimensional surface, rather than genuinely vanishing into an interior at all. Think about how strange that possibility actually is, if it turns out to be true. Everything we've imagined tonight, the stretching, the darkness, the singularity waiting at the center, might be, in some profound mathematical sense, a kind of illusion, a three-dimensional experience generated from information that actually lives, encoded on that boundary we crossed so quietly, so many chapters ago. Not that the experience wouldn't be real, in every meaningful sense that matters to whoever falls in, but that the deeper mathematical truth underlying it might be stranger and more surprising than the straightforward story of falling inward that we've followed this entire journey. Here's the honest, humbling truth about where this stands today. No one knows, with certainty, which of these proposed solutions, if any, correctly describes what actually happens. This remains one of the most actively debated open questions in theoretical physics, discussed and argued over in journals and conferences around the world, without a final, agreed-upon answer. Some of the smartest people who have ever lived have devoted entire careers to this single question, and the honest, complete answer remains, for now, genuinely unknown. And perhaps that's fitting in its own quiet way, because everything we've explored tonight, from the invisible boundary of the event horizon, to the strange bending of light and time, to the unknown singularity waiting at the center, ultimately arrives at the same humbling conclusion. Black holes remain, even after decades of brilliant scientific work, one of the last great frontiers of genuine mystery in our universe, places where our best theories reach their absolute limits, and simply, honestly, admit that they do not yet have all the answers. So here we are, at the end of this long, quiet fall. We began at an invisible boundary, drifted through bending light, felt the first uneven pull of gravity, watched time itself stretch and separate into two different truths depending on where you stood. We crossed a threshold with no alarm, sat with the silence of absolute isolation, and stood at the edge of a mystery even our best equations cannot fully solve. And now, having travelled that entire distance together, it's worth asking what any of it actually means for us sitting safely here, far from any event horizon. Here's the thing most people don't realise about why black holes fascinate us so deeply, keep so many curious minds awake at night, wondering. It isn't really about the darkness itself, or the violence, or even the mystery of the singularity. It's about what these objects reveal, so starkly, about the universe we all quietly exist within. A universe governed by rules so precise they can predict the bending of light around invisible giants, and yet so vast and strange that entire regions remain permanently, mathematically closed off from anything we could ever directly observe. Think about the sheer scale we've travelled through together tonight, from a boundary a few tens of kilometres wide around a collapsed star, to an event horizon spanning billions of miles around the largest supermassive giants known to exist. From a fall lasting mere seconds to one that might stretch across hours of continued awareness, drifting through darkness with nothing left to measure it against. Numbers so large, distances so vast that they stop feeling like measurements at all and start feeling more like meditations on how genuinely immense the universe actually is, compared to anything we experience in an ordinary human life. And yet, here's what remains remarkable. Even after everything we've discussed, we know this, we calculated it, imagined it, wondered about it, together, right now, from an ordinary, comfortable place, far from any danger, using nothing more than curiosity and careful thought, a collection of atoms arranged into a thinking, wondering mind, capable of reaching out across 26,000 light-years to understand the hidden giant at the centre of our own galaxy, capable of imagining, in genuine, careful detail, what it might feel like to fall past a boundary no one has ever actually returned from. There's an old idea, one that captures this feeling better than almost anything else. We are the universe, becoming aware of itself. Every atom in your body was forged inside a star, long before our sun, or our planet, ever existed, scattered across space when that star finally died, eventually gathering together, here into something capable of wondering about its own origins. And tonight, that same gathered stardust turned its attention toward the darkest, most extreme objects the universe contains, and found not simply horror, but a strange quiet wonder sitting right alongside it. This is perhaps the most comforting truth hidden inside everything we've explored tonight. The universe doesn't need to be gentle to be beautiful. It doesn't need to be safe to be worth understanding. Black holes represent some of the most violent, extreme conditions imaginable, places where light itself becomes trapped, where time bends and separates, where our best physics simply runs out of answers. And still, we find them beautiful. Still, we return to them, again and again, drawn by the same quiet curiosity that has always defined us, as long as we've existed. So tonight, as you drift towards sleep, consider this. Somewhere out there, in the patient darkness between the stars, black holes continue their slow ancient work, consuming, bending light, whispering faint traces of radiation back into the cosmos, across timescales too vast for any of us to ever witness completing. And here, on this small quiet world, wrapped safely in your own bed, none of that darkness can reach you. None of that violence touches this moment. You are simply here, safe, resting, part of a universe vast enough to contain such extremes, and gentle enough, tonight, to let you simply close your eyes. Thank you for staying with me on this long, quiet journey into the dark. If you found yourself drawn into these ideas tonight, if this fall through gravity and silence gave you something to wonder about as you drift off, take a moment to like this video or subscribe so more of these journeys can find their way to you. It costs you nothing, and it means more than you know. And so, as you close your eyes tonight, know that somewhere above you, hidden among countless ordinary points of light, a quiet giant waits at the center of everything, patient, ancient, and entirely unconcerned with the small, warm world drifting gently around it. The next time you look up at the night sky, remember what lies hidden within its darkness, and let that vastness settle over you, not as something frightening, but as something quietly beautiful. Sleep well tonight, and keep looking up at the stars. Good night.